Hello, my name is Jesse Nelson,
And I'm Zach Benzerara.
and today we'll be showing you a demonstration of the photoelectric effect using electroscopes. But before we do that, first we'll cover what the photoelectric effect is and some of the events leading up to its discovery.
In the years leading up to the end of the 19th century, scientists started to notice some odd behavior of light. Hertz noticed that if he shined ultraviolet light on a negatively charged electroscope, it would discharge. Around a decade after Hertz made this observation, J.J. Thomson showed that the electroscope was discharging because electrons were being emitted. This phenomenon became known as the photoelectric effect. The following year, Philip Leonard, who was J.J. Thomson's student, constructed a device that consisted of a glass tube with two facing electrodes that were connected to an ammeter. When he shined UV light on the cathode, a current was produced, evident by the reading on the ammeter.
Under the classical model of light as a continuous wave, the energy of light incident upon a material should not affect whether or not electrons are emitted, since the energy being delivered by the light should accumulate over time. However, this is not what Leonard observed. Leonard discovered that in order for the photoelectric effect to occur, the light striking the material's surface must meet some minimum frequency known as the threshold frequency. And if the light does not meet this frequency, then no matter how strong the intensity of the light, no electrons will be emitted. Likewise, if the light does meet the threshold frequency, then no matter how weak its intensity, electrons will be emitted. Leonard also noticed that different materials had different threshold frequencies. The results found by Leonard were inconsistent with the classical interpretation of light.
Near the beginning of the 20th century, Einstein provided an explanation of Leonard's results through a paper he published on the nature of light. Einstein took Max Planck's idea of quantization a bit further by saying that electromagnetic radiation itself was quantized and arrived in small packets of energy that he called light quanta, which we now refer to as photons. In particular, Einstein proposed that the energy of a photon is directly proportional to its frequency and can be described by the following equation: E equals hf, where h is Planck's constant and f is the frequency of light in question.
We can describe the amount of energy needed to ionize a material by its work function, phi. Since the energy of a photon is directly proportional to its frequency, the minimum amount of energy needed for ionization will be directly proportional to the material's threshold frequency, f naught.
Okay, now for a quick example. The work function of nickel is typically provided in the range of 5.05 to 5.35 electron volts. What is its threshold frequency and its associated cutoff wavelength? Remember that Planck's constant has a value of 4.141 times 10 to the negative 15 electron volt seconds. We can use the equation shown earlier that relates a material's work function to its threshold frequency and rearrange it to solve for f naught. After putting in the average value for the work function and Planck's constant, we find the value for the cutoff frequency, which is 1.26 times 10 to the 15 hertz. And then the cutoff wavelength is inversely proportional to the frequency, and since this is a light wave, we will use the speed of light, and after plugging in the values, we obtain a cutoff wavelength of 238.9 nanometers.
Alright, now before we get started, there's a few words of caution we're going to make about the use of the UV lamp. In particular, we want to make sure that we avoid any direct eye or skin exposure to the UV light, and in order to do that, we're going to be using UV protective glasses, and we've also constructed an aluminum shield around the UV light in order to direct the light away from us and toward whatever electroscope that we're working with. In addition to that, we want to make sure that our UV fluorescent light is regulated by an electronic ballast. Now, when you run a current through a gas, such as the inside of the UV lamp, you get new charged particles that are developing, which causes a resistance drop and thus a current spike. And if that current spike in the bulb isn't regulated by an electronic ballast, the bulb is going to burst, and you don't want that to happen.
So we can demonstrate the photoelectric effect using an apparatus that we have constructed here. We have an aluminum shielded UV lamp fixed to a clamp and a stand. We have 3 electroscopes, each labeled 1 negative, 1 neutral, and 1 positive. We will be using rabbit fur and a nylon rod to get a negative charge, and we will be using wool and a glass rod to get a positive charge. Now, if you do not have these materials or would like to use a different set of materials, you can consult the Triboelectric series chart.
Now, a quick note before we go about imparting charges on these electroscopes. As pure aluminum is exposed to air for prolonged periods of time, a thin layer of aluminum oxide will begin to develop on its surface. And this layer will interfere with the photoelectric effect because the electrons will be more tightly bound to the material, and we're trying to strip them away with the UV light. In order to get around this, we can sand the surface of our aluminum conducting spheres with fine sandpaper in order to strip this layer away and expose the pure aluminum underneath.
So the first thing you're going to want to do is take the rabbit fur and rub it along the nylon rod to give it a negative charge. Then you're going to want to impart that negative charge on the electroscope labeled negative by touching the rod to the aluminum conducting sphere, and the charge on the electroscope will be apparent by its foil leaves repelling one another. Now similarly, you're going to want to use wool and a glass rod to give the positive electroscope a positive charge. Now you'll have two charged electroscopes, one negative and one positive, and the third electroscope will remain neutral.
Well, Zach, what do you think might happen if I shine this bright, visible light on each of these electroscopes?
Well, if the light is intense enough, according to classical physics, it should eventually discharge the electroscopes.
That's what you might think, and that's also what they thought at the beginning of the 20th century. But as you can see, each of these electroscopes is entirely unaffected by the presence of this intense visible light. Now, the reason for that is because the cutoff wavelength of aluminum, which is about 300 nanometers, is just outside the range of visible light, which is given from about 700 to 400 nanometers. So in order to see the photoelectric effect, we're going to be needing to use a UV light rated at 254 nanometers, which is well beyond the cutoff wavelength of the aluminum.
Now, while wearing the UV protective glasses, make sure that the UV lamp is facing away from any people in the room, and it is as close to the aluminum conducting sphere of the electroscope as possible. Now, before I plug in the UV light, take a moment to think about the effects the UV light will have on each of the three electroscopes. Now, we're going to start with the positively charged electroscope, and as you might expect, when I plug in the UV light, there is no effect on the electroscope since it is electron deficient, and the photoelectric effect works by emitting electrons from the metal surface. Now, when I move the UV light in front of the neutral electroscope, you might expect a positive charge to develop since electrons are being emitted. But as you can see, there is no apparent effect. When we will give an explanation to this as to why later in the presentation. Now, when I place the UV light in front of the negatively charged electroscope, it discharges, evident by its foil leaves relaxing, since there was an excess of electrons on the metal. The photoelectric effect illustrates the particle nature of light. That light delivers its energy to a material in discrete packets, or photons. Merely increasing the intensity of light, or the number of photons striking a material's surface per second, is not sufficient to cause photoelectrons to be emitted. Instead, the amount of energy being delivered per photon must be sufficient to ionize the material. Although the photoelectric effect shows that light has some particle characteristics, it is also known to act as a wave. This wave-particle duality is explained by quantum mechanics and can be demonstrated through the use of a Michelson interferometer with a set of polarizing materials, as we will show in a future video.
Okay, now let's discuss the behavior of the neutral electroscope in our earlier demonstration by answering a question. Why did the neutral electroscope not appear to take on a positive charge when exposed to UV light? Assume that the radius of the electroscope's aluminum conducting sphere is 8 millimeters, that the wavelength of the UV light used was 254 nanometers, and that the work function of aluminum is 4.14 electron volts. As the neutral electroscope is exposed to UV light and emits photoelectrons carrying a negative charge, we would expect a positive charge, and thus an electric potential, to develop on the surface of its aluminum conducting sphere. This developing potential would increasingly resist the emission of additional electrons. We can describe this developing potential based on the properties of the conductor, namely its charge, which in this case is based on the number of electrons emitted, or Q equals Ne, and its capacitance, which is based on the geometry of the system, and in the case of a conducting sphere, C equals 4 pi epsilon naught r. We'll hold on to that expression for future reference. Now, the maximum kinetic energy of a photoelectron is based on the difference between the total energy delivered to the electron by the incident light and the work function of the material to which the electron was bound. The energy required to ionize the material can be described by the electron's charge and the size of the developing electrostatic potential. We can set these expressions for the energy of the photoelectron equal to one another in order to solve for the maximum electrostatic potential that can develop on the conducting sphere. We now have two equations that describe the electrostatic potential that develops on the aluminum conducting sphere, and we can combine them in order to find the maximum number of photoelectrons emitted by the system. The given information is sufficient to solve this expression. After plugging in the values, we find that the number of electrons emitted is about 4.177 times 10 to the sixth. Since we know the charge of an electron, it is easy to calculate the overall charge that develops on the electroscope at equilibrium. Keep in mind that the charge on the electroscope will be equal to the opposite of the charge of the emitted electrons. After plugging in the values, we find that the charge on the electroscope was 6.68 times 10 to the negative 13th joules. Given the incredibly small magnitude of this charge, it may be reasonable to expect minimal or even imperceptible deflection of the electroscope's foil leaves, so the presence of this negligible positive charge may not have been visually apparent.